Hey everyone, welcome back to another lesson in calculus. Today we're going to be going a little bit further with the chain rule, and the idea is to be able to take derivatives of composition of functions in a much quicker manner than what we developed last time. But before we do that, make sure that you go back and watch that video, because it's so important to understand the fundamentals of why the chain rule works rather than just being able to do it, okay? So, and plus it's gonna help you out in a lot of other contexts later on, especially when we get into U substitution and integration and all of that. So go back and watch that video, and if you remember, if you have watched that video, we developed how the chain rule works by using Leibniz notation, and we basically said that dy dx is equal to dy du times du dx. And so those du's canceled each other out, they reduced, and that's why it worked. But you had to identify u as the inner part of that composition. Well, today I'm going to show you a quicker way to find the derivative using the chain rule. It's just we're just going to look at it through different eyes or through a different lens. We're also going to be just doing a bunch of practice with combining all the rules of differentiation, you know, the product rule, quotient rule, along with the power rule and the chain rule all put together, and that's going to be an important thing. We'll do one application as well later on. So with that said, let's go ahead and get started. A different look at the chain rule. Remember, the chain rule is designed for composition of functions. So if we had f of x equal to g of h of x, now I like writing it like this, rather than the little circle thing for g of, then it is saying that the derivative of f is equal to g prime of h of x times h prime of x. Okay, so this is Newton's form of writing it. It does not explain why it works at all. That's why Leibniz form is so important. But it helps us see it a lot easier, or at least be able to calculate it a lot easier, okay? So here's the main idea. Here's the words that we're going to use. The derivative of a composition is the derivative of the outside function times the derivative of the inside. The derivative of the outside times the derivative of the inside. That's basically all it is. We just got to be able to figure out, identify what the outside is and all that. And we kind of already did that a little bit yesterday, but we're going to do it a lot quicker today, okay? So the derivative of the outside times the derivative of the inside. So let's go ahead and take a look at an example. Let's see, we've got y equals 3x squared minus 5x all raised to the fourth power. Now, let me go ahead and write that down. Y equals 3x squared minus 5x all raised to the fourth power. We want to take the derivative of this. Now, from yesterday, we can identify u. We could say let u equal 3x squared minus 5x. That's the inside, okay? And therefore, y equals u to the fourth. And then we can figure out du dx and dy du. Okay, so the du dx, x is the variable, use the function, that's going to be 6x minus 5. And then dy du, that tells you u is the variable in this case, and y is the function, so that would be 4u to the third. And then when we multiply these two together, the du's cancel out, you're left with dy dx, which is just another way of saying y prime. And so we end up with 4u to the third times 6x minus 5. And so then we plug in the u, so we end up with 4 times 3x squared minus 5x times, cubed, times 6x minus 5. Okay, so that's kind of the long way of doing it, but it explains it pretty well. The short way just says, find the derivative of the outside thing and multiply it by the derivative of the inside thing. Now, this is going to take a little bit of practice to be able to do it quickly, but watch what happens here. What I like to do is I like to underline the inside function. I like to underline the inside function. So when f of x equals g of h of x, the inner function is h of x. But when we look at this example, y equals 3x squared minus 5x to the fourth, the inner function is basically the parentheses. The 3x squared minus 5x. That's the inner function, okay? Now notice when I take the derivative, I'm taking the derivative of the outside thing in respect to the inside thing. So that inside thing doesn't change. It's just instead of g of h of x, it's g prime of h of x, okay? And then we take the derivative of the inside thing. So we're going to take the derivative of the red thing, okay? So let's go ahead and do this. Well, this is how I think of it. The underlying thing, that red thing, I call it something. I just refer to it as something. So what do I have here? I have y equals something to the fourth power. Y equals something to the fourth power. Well, then what's the derivative of that? The derivative of something to the fourth power, using the power rule, is 4 times that something to the third power. Okay? So 4, bring that out in front, times something to the third power, subtract 1 from the exponent. That's great. And notice what we have here. We took the derivative of something to the fourth. We took the derivative of the outer thing, the something to the fourth, and the inside is still the same. So the inside still says 3x squared minus 5x. Okay? Then we need to multiply it by the derivative of that something, the derivative of the red thing. So what's the derivative of 3x squared minus 5x? Well, that would be 6x minus 5. And so you can see that the end result is exactly the same. But there wasn't any work to really do to find the derivative function. Okay? So remember, it's the derivative of the outer thing in respect to the inside times the derivative of the inside thing. Okay, so that's that. Let's go ahead and take a look at a different example here. This actually is going to be a composition of a composition, if you would. So I'm going to go ahead and erase all this to make sure I have room. Not that it takes a lot, but a composition of a composition would take a lot longer probably to do using the chain rule. So I've got f of x, or the longer version of f of x, of the chain rule. So I've got f of x equals 3 sine squared of 2x to the fourth minus 3x. Now if I were to identify, let's just call this y for right now. Y equals, I'm going to rewrite this so I know what I'm squaring. 3 sine of 2x to the fourth minus 3x, and then all of that is being squared. Okay? So you can see that this is a composition on top of a composition, and I believe it's even on top of another composition. Okay? So we would want to identify our u value. The long way, we'd identify our u value. We would say, well, what's the outermost thing? The outermost thing is the 3 and the squared. So let's say that u is equal to sine of 2x to the fourth minus 3x. Then that would imply that y equals 3u squared. So we're good with this. We can take the derivative of this all day long. We got dy du equals 6u. That's easy. But then you notice over here, we have another composition. We have sine of something. So I'll underline the inside of that with green. And instead of maybe using u, I'll use w. So we'll say let w equal 2x to the fourth minus 3x. And that would imply then that u is equal to sine of w. Okay, so now I'm throwing more variables in it, it's making it more complex, but I can now take the derivative of this. This is du. I'm going to run out of room here. I'll do it over here. This is, let's see, u equals sine of w. So then du dw is equal to cosine of w. Okay, we got that. And then because I can just take the derivative of this now in respect to x, dy dx, that's equal to 8x cubed minus 3x. Now remember, our goal is to find the derivative of that. So our ultimate goal is to figure out what dy dx is. So we've got to somehow relate all of these things. How do we do that? We do it by multiplication. We could say that we have dy du times du dw times dw dx. And we can see as a result of that, that the du's are going to reduce, the dw's are going to reduce, and we'd be left with dy dx. So all we have to do is plug in. What is dy du? Dy du is 6u. Du dw is cosine of w. And then dw dx is 8x cubed minus 3x. Now we need it all in terms of x, so we have to replace the u and the w. So u is sine of w. So u is sine of w times cosine of w. Well, I'll just write that down for now. And then we've got to replace the w now. So we got 6 sine of 2x to the 4th minus 3x times cosine of 2x to the 4th minus 3x times 8x to the 3rd minus 3x. So that is my derivative function. That was a lot of work using that method. So let's come up with the shorter way, and I think you'll appreciate it. Again, it's going to take a minute to get the practice that you need with it. But I'll start here in the same place that I did before. First thing, I rewrote it so I got sine of something all squared. And then I also recognize that within the inside function, I have another inside function. Okay? So, how do we take the derivative of this? We take the derivative by saying, okay, y prime is the derivative of the outer thing. Well, what's the outer thing? It's 3 something squared. So what's the derivative of 3 something squared? It is 6 something to the first power. Okay? Then times that by the derivative of the inside. So what's the derivative of the red thing? What's the derivative of the red thing? Well, that would be cosine. So it would be times cosine of whatever's inside the cosine function. So it would be cosine of whatever is inside there. Okay? And then times the derivative of the green thing. And so the derivative of the green thing is 8x cubed minus 3. We'll put parentheses around that. So the derivative of the outer thing is 6 red to the first, 6 red to the first, times the derivative of the derivative of red, so that'd be times cosine of green, and then times the derivative of green, which is 8x cubed minus 3. And then where the red is, I can just replace it with all of that. So it'd be sine of 2x to the 4th minus 3x. And then replace the green with 2x to the 4th minus 3x. And that's exactly what we had before. Okay, so you can see that the work is way, way faster than doing all of that other work. But it's going to take some practice to do this, okay? So with that said, let's see, make sure I'm good here. We could probably simplify that a little bit by multiplying the 6 there, and that's what I did here, but I'm not going to do that, okay? With that said, I'm going to do, I have this worksheet with 11 practice problems on it, and all dealing with combining rules of differentiation. What I want you to do is get this PDF and do it on your own as much as you can, and then come back and watch this video to compare your answers, because it's so important that we get the practice here to make sure we're good with it, okay? So let's go ahead and take a look at number 1. When you're ready, again, do not do this until you're ready. Number 1 is y equals negative 3x to the 5th minus 1 to the 4th. So this is a chain rule because we have a composition. So we're going to underline our inside. So what do we have? We have something to the 4th. What's the derivative? The derivative is 4 something to the 3rd. Okay? And then times the derivative of the something, the derivative of the red thing. So it's going to be times negative 15x to the 4th. That's it there. And then on the inside, we rewrite the red value. Okay? And then we can simplify that a little bit to say y prime equals negative 60x to the 4th times negative 3x to the 5th minus 1. So that is number 1. Okay? Number 2. Number 2, we have f of x equals the third root, the cube root, of 4x to the third minus 7. Well, before I go any further, I'm going to rewrite this as a rational exponent so that I know that I take the derivative correctly. So this looks a lot like number 1 because now we have just exponent and power rule. So what's the inside function? The inside function is 4x to the third minus 7. So the derivative of the outer thing is going to be 1/3 times whatever's inside raised to the negative 2/3 power, because we're just using the power rule, and then times the derivative of that inside thing, so it'd be times 12x squared. And then we just rewrite the inside thing there. Okay, simplifying that a little bit, we end up with 4x squared times 4x cubed minus 7 to the negative 2/3 power. So that's f prime of x. Okay, so that's number 2. For number 3, we have y equals, oh, I like this one. This one goes a little bit more intense. 3x to the third plus 1 times negative 4x squared minus 3 to the fourth. Okay, so one step further here. You guys should recognize that you have a product. We are multiplying two things here, but we also do have a composition because we have something raised to the fourth power. So the last thing we're going to do essentially is multiply. So that's the overarching rule that we're going to apply. So we're going to find the derivative using the product rule. So this is my first function in the product. This is my second function. And so remember the product rule said the derivative of the first thing, which is 9x squared, times the second thing, so negative 4x squared minus 3 to the fourth. So that's derivative of the first times the second, plus the derivative of the second thing. So I'm just gonna leave that blank for now, times the first thing, so times 3x cubed plus 1. Okay, so I have to figure out the derivative of this second thing. So I'm going to write that down separately. And if you were doing good on number 1 and 2, you should be able to figure out the derivative of this pretty easily as I drop my marker. And so what's the inside thing? We're going to apply the chain rule here. The inside thing is negative 4x squared minus 3. The outside is something to the fourth. So it'll be 4 times something. So that would be 4 times negative 4x squared minus 3 raised to the third power, and then times the derivative of the something, so times negative 8x. Okay, so that is the derivative of that second piece there. We could simplify that a little bit by saying negative 32x times negative 4x squared minus 3 to the third. Okay, and not much reason to simplify that further other than to maybe say minus there. Okay, so that's number 3. That applied the product rule and the chain rule together. That's a good example there. Number 4, we have y equals, x cubed plus 4 to the fifth power all over 3x to the fourth minus 2. So we're looking for the derivative of that guy. Notice we have a quotient and then we have a composition on top. So we've got to figure out the derivative of the top thing. So I'm going to kind of go a little bit quicker here. The outer thing is something to the fifth, so the derivative of that would be 5 times something, in this case x to the third plus 4, to the fourth, times the derivative of the inside, so that would be times 3x squared. Okay, so that's the derivative of the top. Then remember times the bottom, minus the derivative of the bottom, which is 12x cubed, times the top, so that'd be x cubed plus 4 to the fifth, and then all over the bottom squared. Now, can I reduce some of this? Maybe. I can see that there's an x to the third plus 4 and an x to the third plus 4, so I could take that out as a common factor if I find that beneficial, but I'm not going to go ahead and I'm not going to simplify that any further than that. All right, so those are the first 4 problems in that document. What I would like to do now, I'll get to the next 4 or 5 in a little while. I want to go on to talk more about the lesson and go over the application problem that I have here. So let's go ahead and go to that next slide. Okay, so an application, it looks like we have a particle motion problem because we're talking about x of t. So a particle moves along the x-axis such that x of t is essentially its position. Describe what the particle is doing when t equals 4 pi over 3. When t equals 4 pi over 3. And I said, hint, find the position, find the velocity, and find the acceleration all at 4 pi over 3. Because if you remember, all of that combined, if I start comparing those things, is going to give me whether the function is, whether the particle is speeding up and slowing down, which direction the particle is going. Is it moving towards the origin or away from the origin? So all of these things can be determined by finding the position, the velocity, and the acceleration. So let's go ahead and write this function down. We've got x of t equals 2/3 cosine cubed of t minus 4. And I'm going to put parentheses around that t so I know that that is what I'm taking the cosine of. And then I'm going to rewrite this a little bit because I don't like where that cube is. It doesn't really tell me what I'm doing. So it's actually cosine of t and then cubed minus 4. Okay? So in the hint, I told you to find the position, velocity, and acceleration. So let's go ahead and find the position here. So we would find x of, what was the point? 4 pi over 3? X of 4 pi over 3. Well, that would be 2/3 times cosine of 4 pi over 3, all cubed, minus 4. Simplifying that, that would be 2/3. Let's see, cosine of 4 pi over 3, that is, what is that? 4 pi over 3, that's way down here. That's going to be negative 1/2, I believe, negative 1/2 cubed minus 4. So that's 2/3 times negative 1/8 minus 4. So that's going to be 2 over 24, negative 1 over 12, minus 48 over 12, I believe. So we get negative 49 over 12. That's my position. Boy, that was a lot of work just to find the position. Okay, so that's the position, just plugging it in. The main thing is that I know that the position is negative. I'm going to go ahead and write that down over here so I don't forget about it. 2/3 cosine of t to the third minus 4, and I know that x of 4 pi over 3 is equal to negative 49 over 12. I hope I didn't make a mistake in that. Okay, so that's my position. Now let's go ahead and talk about the velocity. Okay, the velocity, remember velocity is the derivative of position. So we need to take the derivative of that guy. And well, what do I notice? I notice that I have a composition of a composition in a sense. I've got something raised to the third power, and then I have the cosine as that something. So remember, the derivative of a composition is the derivative of the outer thing. So let me underline the inner thing. And usually you can tell by parentheses or brackets. The inner thing is cosine of t. So the derivative of the outer thing, what's 2/3 times 3? Well, that's 2. And it'll be 2 something to the second power, right? And that something is the cosine of t. Okay? And then the derivative of the negative 4 is 0. So we took the derivative of the outer thing. Now we need to multiply by the derivative of the inner thing. Well, the derivative of cosine of t is negative sine of t. And then we can simplify that a little bit to say negative 2 cosine of t squared times sine of t. Okay, so that is my velocity. And of course, I want to find the velocity at 4 pi over 3. So that's going to be negative 2 times cosine of 4 pi over 3, and then all squared, times sine of 4 pi over 3. And then simplifying that, cosine of 4 pi over 3, cosine of 4 pi over 3 is, again, negative 1/2 squared. And then sine of 4 pi over 3 is going to be negative rad 3 over 2. And then we can simplify that. That's going to be 1/4 times negative 2 is negative 1/2 times negative rad 3 over 2. And that simplifies to rad 3 over 4. So we have the velocity now at 4 pi over 3 equaling rad 3 over 4. Rad 3 over 4. So now we have our position and velocity. We can actually answer a question based on that. But let's go ahead and find our acceleration now. Well, our acceleration is going to be the derivative of this. So let me go ahead and write that down. Acceleration is the derivative of velocity. Okay. Now, what do we have here? Well, we have a product and we have a composition. Okay. So the first piece of this product is negative 2 cosine squared. And the second piece of this product is sine of t. So we need to figure out the derivative of the first thing. And the way we're going to do that is the chain rule. So the outer function is negative 2 something squared. The derivative of that would be negative 4 something to the first, then times the derivative of the something, so times negative sine of t. That's the derivative of the cosine of t. So that is the derivative of the first thing, then times the second thing, so times sine of t, and then plus the derivative of the second thing, which is cosine of t, times the first thing, which is negative 2 cosine of t squared. Okay. Now I'm going to clean all of that up a little bit just to make my life easier. A of t is going to be equal to, well, we got a negative times a negative is a positive, so we have 4 cosine of t, and then here we have sine squared, so times sine squared of t. And then here I've got negative 2, so minus 2, and then this is actually going to be cosine to the third, right? Cosine of t times cosine of t squared. So that's the acceleration here. And then we're going to plug in 4 pi over 3 and get our answer for acceleration. Sine squared of 4 pi over 3 minus 2 cosine cubed of 4 pi over 3. Okay. Well, what's cosine of 4 pi over 3 again? That's going to be negative 1/2. Sine of 4 pi over 3 is negative rad 3 over 2, and we're squaring it. Minus 2 cosine of 4 pi over 3 again is negative 1/2, but this time we're cubing it. So we end up with negative 2 times, that's going to be 3 over 4. And then here we're going to get plus, because negative 1/2 cubed is negative 1/8, times 2 is positive 1/4. And so this is negative 6 over 4 or negative 6 over 4 plus 1 over 4, which is negative 5 over 4. So we have our acceleration is negative 5 over 4. So let's go ahead and write that down. Negative 5 over 4. All right, so we have all the values of our position, velocity, and acceleration. And I'm going to go ahead and leave the work up for my derivative of position and my derivative of velocity. But I want to go ahead and interpret these three values here. What does the position being at negative 49 over 12 imply? Well, here is the origin. That position tells me that I am on this side of the origin. Okay, so I'm on the left side of the origin. I could say that. Okay, so I would conclude with this. Left side of origin. Okay, left side of origin. And since the velocity is positive, that means I'm moving to the right. So I would say moving right. Okay, oops, moving right. And I would justify that since v of 4 pi over 3 is greater than 0. Okay? But I can add one more step to that, or one more idea. Since I'm to the left and I'm moving right, that means I'm moving toward the origin. So we could say moving toward the origin, and then that would be since v of 4 pi over 3 and x of 4 pi over 3 have opposite signs. Okay? So we can see since position is negative, it's over there. Since velocity is positive, it's moving that way. So we are moving toward the origin because they're different signs. Okay? Then we can now compare velocity and acceleration, and we notice that velocity is positive and acceleration is negative. So what does that mean for us? Well, we should have this in our brain, but we want to visualize it too. Since velocity is positive, we're moving that way. Since acceleration is negative, it's a force that's pushing against me. It's pushing opposite to the way I'm moving, which means I'm going to slow down. So we would say the particle is slowing down, and the justification would be since v of 4 pi over 3 and a of 4 pi over 3 have different or opposite signs. Okay? So we are looking for all of those things when we're talking about particle motion. We know we're on that side of the origin. We know we're moving this way, so we're moving toward the origin. We know since we're moving that way and acceleration is pushing against us, we're slowing down. So we're moving to the right and slowing down on that side of the origin, moving toward the origin. Lots of information there. But let me go ahead and make sure that I did this right. Hey, look at that. I got my position right. Got my velocity function right here. That looks good to me, and that simplifies. So we end up with, come on now, we end up with rad 3 over 4, got that. And then we take our acceleration, which is a combination of the product rule and the chain rule. And so we end up with, see if I did that right, negative 5 over 4, perfect. And then we can interpret that. We know that we're on the left side of the origin. We know that we're moving to the right, and that means we're moving toward the origin because velocity and position are opposite signs. And we are also slowing down since velocity and acceleration have the same signs. All right, so that was a great example of rules of differentiation and the application of those rules. Okay? So with that said, I'm going to go over just a couple more on this practice. And if you have any questions on any of the other problems within this practice, then feel free to reach out by commenting or getting a hold of me in a tutoring session, and I can help you out with this. Let's go ahead and take a look at, well, let's do number 5. I like number 5. Because it involves trig. So we have f of x equals cosecant of 2x to the third. So we want the derivative. We recognize that this is going to be the chain rule because we have a composition. We have something inside of something else. So now we have to remember the derivative of cosecant. Remember all co-functions in trigonometry, cosine, cosecant, cotangent, all have a negative out front of them, okay? And then we repeat the cosecant. So the derivative of cosecant is negative cosecant times cotangent. And then, of course, the arguments, the things inside are 2x cubed. Those remain the same, okay? So the derivative of just the outside, the cosecant, is negative cosecant of something times cotangent of something. Then we need to multiply by the derivative of the something. So the derivative of the inside is 6x squared. And then we could simplify this a little bit by putting the 6x squared out front. So negative 6x squared, cosecant of 2x cubed times cotangent of 2x cubed. And that is number 5. All right. What else? What else do we have here? Let's go ahead and look at, how about we do number 10. Number 10 is a good one. F of x equals sine cubed of x to the 5th. And so we can rewrite this, first off, by saying sine x to the 5th, all raised to the 3rd power. And then taking the derivative of this, we recognize the composition. We actually recognize multiple compositions. So we would say the inside is sine of x to the 5th. So the outside is something to the 3rd, so that's 3 times something, to the 5th, squared, then times the derivative of that something, but recognizing, since I just wrote down that something over again, I'm just going to go ahead and underline it here. So what's the derivative of sine of x to the 5th? Well, the inside of that is x to the 5th. So then the derivative of sine is cosine of x to the 5th. And then times the derivative of x to the 5th, which is 5x to the 4th. Simplifying that a little bit, we got 15x to the 4th times sine of x to the 5th, all squared, times cosine of x to the 5th. And of course, you can move that square right here if you want to, but there's no real need for that. All right, so that is number 10 on that worksheet. And there's a few more to do. Again, you should probably try and do those on your own. And if you have any questions, reach out to me. Number 11 on there is just like the example that we did on the lesson with the particle motion and describing what took place. But with that said, I hope you have a better understanding of how to apply the chain rule, or at least a quicker way of doing it. And of course, if you get stuck with this, you can always revert back to the actual Leibniz form to help you see it. But the idea is to be able to rattle off these derivatives pretty quickly. We have covered a very significant amount of functions and taking derivatives of those functions. We've covered pretty much all the rules. We just have to focus on a couple more functions, specifically the exponential function and the logarithmic function, and then we'll also get into inverse functions after that. But we've covered the main basic ones, you could say. And like always, if you have any questions, please comment below. Don't forget to hit that like button, because I know that you like these videos, or maybe you don't, but even if you don't, you can hit like. Otherwise, I'll see you all later.